Okay, let me show you one more way you could have solved this game. Okay, maybe you didn't want to engage in this iterated dominance reasoning to found the solution to this game. Here's another way. You could have used the Nash equilibrium idea to find any point in this game table that's in Nash equilibrium. One way of applying Nash equilibrium, you'll remember, is to apply that mini-max test, where you look at each particular row, you find the minimum value in that row, and you also look to see if that same value is also the maximum value in its column. So let's look at row 1. The minimum value in row 1 is 2 there and 2 there. That's the minimum value in row 1. But the 2 here is not the maximum value in its column. 7 is. However, the 2 here is also the maximum value in its column, so that particular point passes the minimax test for Nash equilibrium. But now look, we need to check here again too. Here's another one that is the maximum value in its column. But notice that it is not the minimum value in its row, 2 as opposed to 1. So only this particular point is in passes the minimax test for Nash equilibrium. And so this particular point is the only point on this game table that is in Nash equilibrium. If the players get onto this point, neither has unilateral strategy for unilaterally changing his or her choice of strategies. Column would not gain anything by changing strategy. It would either do the same at -2 or go to something worse, -4 or -5. Row would not do any better. Row would either do worse by going from +2 to +1 or from +2 to +2. So that point is in Nash equilibrium. You could also have found that point thinking about the other way of testing for Nash equilibrium, the security strategies for each. That is, you look and see what is the security, what is the worst outcome that could happen if row played each of these strategies. Well, the worst thing that could happen to row by playing this strategy would be an outcome of +2. The worst thing that could happen to row by playing this strategy would be an outcome of +1. The worst thing that could happen to this strategy, row played this strategy, would be an outcome of +1. So this is row's security strategy. The worst row is going to do by playing R1 is +2 as opposed to +1 and +1. For column now, we can look and see. Column's security strategy is to not play C1, right? Because column could do as bad as -7 as opposed to -2, as opposed to -3, as opposed to -1 by playing C4. Okay, so therefore only this point right here is opposed to -1. Only this point right here is the combination point of columns row's security strategy and column security strategy. So again, that's the only point on this table that is in Nash equilibrium. And so once again, you could have either have used the iterated dominance reasoning that found this point, or you could have used any of the 3 ways of finding Nash equilibrium to find that point as the unique, pure solution to this game, R1, C2, with a value of 2 for row, and so a value of -2 for column.